by A1 times epsilon 1 is left in the denominator, bring it up to the numerator. This is A1 epsilon 1 sigma T1 to the power 4 T2 to the power 4, and we have proved what we assumed at the beginning of the semester. So life comes a full circle always for all of us. There's no escape from that. So this is quite nice, isn't it? Of course, there are some assumptions involved. What are the assumptions? Is that the surface is opaque, surface is diffuse and gray, and we always said at the beginning of the semester that our surroundings are large. What does that large imply? The large implies that this area A2 is much, much larger than A1. And under these circumstances, this is a completely valid formula to use, simplifies your life by a great margin, and it is actually not too far away from the truth. And mind you, in doing so, we have not assumed that the surrounding is an ideal body. This surrounding could have whatever emissivity it wants to have. I am not doing any restrictive acts on the surrounding. All I am concerned about is my surface, which is opaque, diffuse and gray. If this is true, good to go. Do not care what the emissivity of the surrounding is. It can be whatever it is, as long as it is very large. Okay? And I think this is a good place to stop the lecture. And in my opinion, radiative resistances are the crowning glory of heat transfer. And maybe before we leave, I want to point out one more thing. Why is this not the same as conduction and convective resistances? Is because in conduction and convection, remember, Q conduction was delta T by R. It was delta T by R, and that is more reminiscent or more representative of the voltage difference by the resistance. Here, this is a little bit of a stretch. We are saying that this is the difference in the emissive power. And if you assume that this is obeying Stefan-Boltzmann law, it is T to the power 4 minus T to the power 4. It is not the same as delta T. So you cannot conflate the idea of thermal radiative resistances with conductive and convective resistances. And what we are going to do from the next class is we are going to look at all of these different modes coming together. When you do that, you will have to handle radiation separately because it has its own resistive network. Get some information from that resistive network and throw it onto the other two resistances after you do all these manipulations.